Okay, so what we're going to be going over is how to find the area underneath a curve. Now, let's say we have this function. This is the function x squared. Let's say we want to find the area underneath the curve from x equals 1 to x equals to 3. Now, this isn't a shape that we really know how to find the area for. You know, it's not a triangle. It's not a rectangle. So we're a little bit of a loss. We don't have a formula for it. So then we go, what if I want to approximate it? So then you think, well, if you were to approximate it, you would have to use a formula for something that you already know. So what we're going to do is we're going to use rectangles to approximate it. Now, we're going to start off with a small number of rectangles. Let's say we're going to start off with 2 rectangles. And let's see what this looks like. So, we're starting off really basic, just step by step. So if I draw 2 rectangles from 1 to 3, that means that each one is going to have a width of 1. So the width is equal to 1. And so let's say I start off right here and I draw 1 rectangle. And then I go up at 2 and I draw another rectangle. So if I find the area of this rectangle, so this area is going to equal to the height here, which is 1. The width is also 1. So this is going to equal to 1 plus the height of this one is 4. And the width is 1. So it's equal to 4. So the area is 5. So notice that this is, it's not actually very close because, we've got all this dead space over here. So this is we're going to call this a left-hand approximation. Now, if you wanted to do a right-hand approximation, you would do the same thing, except that you would start 1 over. So instead of starting at 1, we're going to start at 2. And then we're going to go backwards. So the right hand, let me put a little r here. We have this first rectangle, the area is 4, and then we go over 1 more and draw another rectangle. And the area of this one is going to equal to 9. Okay, so notice that what we have is this one right here, the second one we found. This one is an overestimate, and this one is an underestimate. Okay, so then you go, well, what if you want to do better? I mean, 5 and 13, it's probably somewhere in between. And you might be thinking, well, what if we average them? Well, yeah, you could average them, but still, you don't really know how close you are. The idea is that we want to get a better approximation, as good as we can get. So then you might say, okay, well, what if we do more rectangles? Instead of 2, let's do 4. How about 4? So let's see what this looks like with 4 rectangles. Now, if you're going to do 4 rectangles, well, they have to be twice as narrow. So now they're going to be of base 1/2. So that's the width. And so you're going to have, you're going to go over 1/2. And then at that point, you go up again. And then over. And then you go up again. Over. And then up again. And over. Now notice, so this is a lot better than the previous example. So I'm going to use the proper notation now. Actually, depending on what book you have, it's going to be different. But Since we're doing 4 rectangles, and this is called the left-hand approximation, we're going to use L and then a little 4 here. Okay, so this is notation for left-hand approximation with 4 rectangles. So the area of each one of these, the area of this one is going to be 1. The area of this rectangle, 1 times 1/2, because the height is 1, and then 1/2 is the width. And then this one is going to be 1.5. The height of this one is 1.5 squared times 1/2. The height at 2 is 4 times 1/2. The height at 2.5 is 2.5 squared times 1/2. Or you could just leave them all as fractions if you want. And so if you add up all of these, you'll get 27/4, or about 6.75. Okay, and then if you do the right-hand approximation, which we are going to call R sub 4, so that's going to equal to, so let me draw them first. So to do the right hand, basically what you do to start off is, instead of starting at your starting point, you start one rectangle over. Let me pick a different color. So we're going to start at 1.5, and then you go up, and then you go backwards in this case. And then at 2, we're going to go up and then backwards. And then at 2.5, up and backwards. And then at 3, up and backwards. Okay, so let's put in the areas. The area of this first one is going to be 1.5 squared times 1/2. Maybe I'll just do it over 2 instead. And then the height of the second one is going to be 4, and then over 2, because it's times the width, which is 1/2. And then 2.5 squared over 2. And then 3 squared, which is 9 over 2. And so when you add all of those together, you get 43/4, which is 10.75. So notice that these two are closer than what we had before. And another thing to notice that I want you guys to realize is, notice how both the left and the right hand approximation, notice how they share some of the same rectangles. So this is just something to note. See how they share the rectangle. All the rectangles in the middle are shared between them. The only ones that they're different by are the very first rectangle for the left-hand approximation and the very last rectangle for the right-hand approximation. So that's how far off they are. Okay, now you might be thinking, well, what if you want to go do better than this? You want to do, instead of 4, you can do 8 rectangles. How about 16? How about 32? How about 1 million? Take a guess what you need to do to find the exact area. The exact area is equal to how do you find the exact area? How many rectangles do you need? How many rectangles? That is correct. Infinitely many. Infinitely many rectangles. Rectangles. Okay. Infinitely many rectangles. Okay, so then how do you do that? So, obviously you can't add up infinitely many rectangles. Well, the only way that you can explain adding up an infinite amount of rectangles would be with limits, right? You need limits. So, okay. So what we're going to do next is we're going to go over some really important notation, math notation, so that we can develop the formula to actually find the area underneath the curve. So let's do that now. Okay, so what I've done is I've just made this picture smaller, and so we're just going to use this as a generic function. Now, I'm going to write down over here, we'll keep track of the notation because we're going to need to sort all that out. So it's really important to understand what everything represents. Now, I'm going to draw just our first, so I'm going to make it a small, just 2 rectangles, just for now, for demonstration purposes. And the width of the rectangles, is symbolized by delta x. So delta x is the width of your rectangles. Okay, and then notice, so we're going to call the points where the function is evaluated, we're going to call those x and then sub 0, and then the next one is going to be x sub 1. And so in general, what you call those is you're going to say x sub I. Now I, that's called an index, and use that to denote, for example, x sub 0 is the, the index is 0, but it represents the first one in this case, and then x sub 1, that's the next one, x sub 2 would be the next one, x sub 3 would be the next one, and so on and so forth. So the more rectangles you have, the more of these indexes you would have. So this is the, we're going to say this is the ith x value. Okay, now notice that if you find the value of the function, so right here, for example, this right here would be f of x sub 1. This is the height of the rectangle at that point. So f of x sub I represents the height of the ith rectangle. Okay, and then a couple more. N, capital N, is going to represent the number of rectangles that you're going to use. And then A, the letters, the constants A and B, those are going to represent the interval. So this is the start of the interval, and B is going to be the end of the interval. Okay, so in this example, so just to kind of put this together with the example that we just did, delta x in this case, with what I drew right now with 2 rectangles in this example, delta x would equal to 1 because that's the width of the rectangle. X sub I would be, the values of x sub I would be 1 and 2 because those are the x values where you're evaluating. F of x sub I is what you get when you plug in those values into the function. That represents the height of the rectangles. So that would be 1 and 4. Capital N, the number of rectangles, that would be 2 in this example. And then A is the start, which would be 1, and then B is the end, which would be 3. Okay, so just to kind of put it in context. Okay, so then you need to remember the, I'm going to write down the formula for the approximation. So the area underneath, okay, so this is going to get a pretty crazy. The area underneath the curve is approximately equal to the sum from 0 to n minus 1. I'm just going to write down the formula and then I'm going to explain it to you guys. So f of x sub I times delta x. So let me relate that to what we just did. This right here is basically, remember, this is the notation for sum. So this is saying that the left-hand approximation is this sum from going from I equals to 0 to n minus 1 of f of x sub I times delta x. So notice how this right here represents the height of the rectangle, and this represents the width. And so basically, this says, for example, the first one would be f of x sub 0 times delta x. So that makes sense, right? Because x sub 0 is right here. So f of x sub 0 represents the height, and then delta x represents the width. So that gives you the area of this first rectangle. And then you increase the value of I, so you would go then to f of x sub 1 times delta x. And so that makes sense, right? Because x sub 1 is right here. So f of x sub 1 is the height, and then times delta x. That gives you the area of the next rectangle. And so depending on what n is equal to, this is the formula. So it's basically what we just did intuitively. It's put into a formula. Okay, now, it's about to get a little bit more confusing, because when you do the right-hand approximation, the idea is the same. So I'm going to write down the same formula. F of x sub I times delta x. But the index is different. See, x sub 0 is the same spot as a. But if you're doing the right-hand approximation, remember you want to start 1 over. So the index for the right-hand approximation is going to go from 1 instead of 0. And it's going to go up to n instead of n minus 1. So it's just basically, the only difference really is that you're just starting over 1. So here, if you were to expand it the same way, you would get, let me write it out, f of x, since you're starting at 1, it would be f of x sub 1 times delta x. So if I go back to my picture, you would start here, notice, and then times delta x. So see, that's the first rectangle of the right-hand approximation. And then plus the next one, f of x sub 2 times delta x. So then you would go, the next one, this would be x sub 2. So you would go up and then times delta x. And so notice this matches up with what we did earlier in our just basic example of the right-hand approximation using two rectangles. Okay, now here comes the awesome part. Okay, you guys ready? Ready, ready, ready. Ding, ding, ding. Okay, so we said, remember, that we wanted infinitely many rectangles. Infinitely many. So, whoa, this is crazy, crazy, crazy. So you want infinitely many. This isn't infinitely many. This is more, but that's what we want. So notice what we want is the number of rectangles to get bigger and bigger and bigger each and every time. So let me go over a tiny bit more here. So the exact area is equal to any one of these. Whichever one you want. Let's do the right hand. It's exactly the same formula for the left hand. So you take this one, the right hand, let's say, this formula. And then the only thing you have to do, now that we've developed all this theory, the only thing, this is crazy, the exact area is given by the limit as n goes to infinity of that sum right there. So basically what you're saying is that you're going to get infinitely many super thin rectangles. And when you add all of those up, what's going to happen is you're going to get the exact area underneath the curve. Okay, so this has a special name. This is called the infinite Riemann sum. Okay. Now, before we can actually calculate one of these, you need to know a couple of important formulas, some formulas. So what we're going to do is I'm going to state the formulas, and then I'll let you, we're going to do an example. Okay, so here are the 5 formulas that you're going to need. You can look up all of them if you don't believe me. But basically, this one says, the first one says that if you're the sum of 2 different terms, you can split it up into 2 separate sums. That makes sense. This one says that if you have a constant times your sequence, that you can take that constant outside of the sum, which is basically the same as factoring. This one says that if the sum of k from 1 to n is equal to n times k. That makes sense because you're adding up k a bunch of times. These 2 are really fun. You can look up the proof of these, but they're great. This one, Gauss came up with it when he was a child. Forget how old he was. It's an interesting story, so you might want to look that up for fun. So we're going to use all these, and you'll notice that it takes a really, really, really long time to actually find this infinite sum that we had, this formula. So the whole point of this is to realize how much easier we're going to make this incredibly complicated formula. We're going to make it incredibly simple using calculus. So that's what's coming.